Welcome to this NPTEL course on robotics, basics and advanced concepts. In this week, we'll look at applications of parallel robots. We had looked at the kinematics of parallel robots in the last week. Now we'll see some applications. Okay, so there'll be 3 lectures in this part. The first lecture deals with sun tracking using a 3 degree of freedom parallel robot. In the second lecture, we'll look at Stewart-Gauss platform based force torque sensor. And in the third lecture, we'll look at vibration isolation using a Stewart-Gauss platform. Okay, so the 3 degree of freedom parallel manipulator and the Stewart-Gauss platform, okay, is also our Stewart-Gauss platform is also a parallel manipulator, and it is one of the most well-known parallel robots. So quick acknowledgement, most of this work was done by my students in the robotics and design lab. So there is Ashit, there is Mohit, there was a visitor from Sweden, name of Nils, and then Sudipta and various other students. Okay, the funding came from this Indo-US project called Sirius. Okay, so the contents of lecture 1, we'll just introduce sun tracking initially, then we'll see some of the main configurations, standard configurations which are used for tracking the sun. Then I will show you how we can also track the sun using a redundant parallel robot, and then conclusion. So let's start. Okay, so solar energy harvesting is a very important and upcoming field. Okay, we need to generate clean energy. We don't want burning coal or gas because it is causing global warming. We are increasing the percentage of carbon dioxide in the environment, which leads to global warming and various problems in climate. So solar energy is one of the cleanest source of energy. To harvest this solar energy and convert it into something useful form, there are various approaches. One is this thing called flat photovoltaic panels. Okay, so basically this is a picture which shows that there is this huge field of panels, PV panels, which are laid out in the field. Okay, so they will convert the incident solar energy to electricity directly. They typically have efficiency of the order of around 18 to 20%, although there are some newer ones which have higher efficiency. One of the problems of solar energy is that you need to store the energy when too much is produced. Okay, so in this PV panel, you need to store the energy using batteries or some other form, because when the sun is not there, you still need to supply energy, and then the energy from the storage medium is sent back to the grid. PV panels and solar energy using PV panels is becoming very competitive. Okay, it is almost the same price as coal. So in this figure, this is a site in Andhra Pradesh in Kurnool, and it is rated to produce 1 gigawatt of electrical power. Okay. We can also have another way to harvest solar energy. This is called as parabolic trough. So what happens here is the sun's energy, which is coming onto these mirrors, they are reflected onto a central focus. Okay, so in this focus or in this tube, there are this water or some fluid which is running. Okay, and that fluid can be raised to a higher temperature, and then that steam or some other fluid is taken out and it is used to run a generator. Okay, so the tube is at the focus, and as the sun moves, this parabolic trough is rotated in the east-west direction. This has an efficiency of the order of 20%. There is also something called as a dish concentrator. Basically, it is a dish which is in the form of a parabolic dish, and at the center or the focus of the dish there is a device, okay, which can convert thermal energy to electrical energy. Okay, so most of the time it is something called as a Stirling engine. So the advantage of this is that this parabolic dish concentrator, or this dish, can track the sun in two directions. It can track in the east-west directions, and it can also track the seasonal motion of the sun. Okay, it also has much higher efficiency than PV or parabolic trough. You can have efficiency of the order of 30%. So this is the efficiency of the incident energy to the amount of electrical energy that is produced. One more way of generating electricity from sun's energy is something called as a concentrated solar power tower. Okay, so the left hand side shows a picture of lots of mirrors which are moving and focusing their energy onto a central receiver. Okay, so unlike the parabolic dish, all this mirror energy coming onto the mirror and reflected comes to this central tower. Okay, so this is called as a power tower, and this is called concentrated solar energy, solar power tower, because all this energy which is coming in each of these mirrors are concentrated at this receiver. Okay, so as I have shown you, this is many mirrors are there, and they need to move to track the sun, and the incident energy will go and hit this tower. Okay, this is being implemented in many places because of a few advantages. So it has been implemented in Spain, US, Australia, Middle East, China, and various places. So what is the setup? They have large number of mirrors. These are also called heliostats. They will track the sun and focus energy at a distant receiver. Okay, so the distance between this central tower and the last mirror could be as much as 1 kilometer nowadays. Okay, now since there are so many of these mirrors which are focusing the energy onto a tower, the temperature of this receiver can go very high. Okay, it can go to 600 or even more higher, 600 degrees centigrade or even higher. Okay, and as a result, since the temperature is high, the conversion of thermal energy to electrical energy is also more efficient. Okay, so you can easily get more than 30% efficiency. Another big advantage of this concentrated solar power tower scheme is that you can store the energy as thermal energy. So you can have what are called as molten salts or some other way of storing the energy in a thermal form. So when there is no sun, okay, we can recover that energy and continue to run the generators and power the grid. The challenge in this setup is that the motion of the sun is very slow. Okay, so typically a sun moves up of the order of 180 degrees in 12 hours in the east-west direction, and it also moves some 30-40 degrees depending on which latitude you are on in the north-south direction. The other big challenge is we need to make sure that we track this sun and point this reflected beam very accurately. So we have to move this mirror very slowly, but at the same time very accurately. How much accuracy? Typically we need of the order of 5 milliradians. Why? Because if you think of a mirror as, let's say, 1 meter by 1 meter, and this is 1 kilometer away, and you can see that if you want to focus the beam onto some area of this receiver, okay, then if you are off, then the reflected beam will go somewhere else. Okay, so typical accuracy requirements are of the order of 5 milliradians. So the main challenge is we need to move these mirrors in 2 axes very slowly but very accurately. A typical setup of this solar power technology is the following. So we have this mirror, also called as a heliostat. The sun's energy is reflected from the surface of this heliostat. It will go to a receiver, okay, and typically this output of the receiver could be shown here 565 degrees centigrade, but it can be even higher. So we store the energy in hot salt or storage tank. Then we convert that to steam by means of a heat exchanger. Okay, and then we run a generator and convert it into electricity to feed into the grid. Okay, the output of this storage, cold storage tank, is much lower, and after the receiver it is much higher. Okay, so it turns out that the heliostat cost is a significant cost of this whole setup. Okay, so according to this researcher Kolb, okay, it is of the order of 50%. And in 2009, he had said that we need to lower the cost of this heliostat to less than $80 per meter square. Okay, so in order to be competitive with coal and wind and various other forms of energy. Okay, he had said that it shows very high potential. Okay, and this was another researchers in 2012. He claimed that this is much more potential than, let's say, PV. Okay, that may or may not have come true, but nevertheless, it's a very challenging and very potential technology to convert sun's energy into electricity. There are various existing heliostats. There is one which is called the azimuth elevation heliostat. So basically, it has 2 degrees of freedom. Okay, the sun moves east, west, and north, south. So you need 2 degrees of freedom or 2-axis motion. So one motion is this azimuth. You can rotate by this, and there's other one is this elevation. Okay, so sorry, this is the elevation and this is the azimuth. So what happens is the incident rays comes and it gets reflected according to the laws of reflection. So this is the normal to the mirror. Okay, so what do we need to do? As the sun is moving, we need to rotate this mirror such that the normal is in between the incident ray and the reflected ray. The reflected ray is fixed, right? Because the location of the receiver is fixed in the field. So only thing is the incident ray direction is changing, and then we have to suitably change the normal to the mirror. And there are these laws of reflection which says that these 3, normal, incident ray, and reflected ray, should be in the same plane, and the angle of incidence should be equal to the angle of reflection. So the location of the sun or the location of the incident ray is known. It depends on latitude, longitude, time of day, and the date in the year. So the incident ray is fully known. Okay, the location of the receiver is also fully known. Okay, so hence all we need to do is change the mirror normal by doing these 2 motions such that the properties of reflection are satisfied. Okay, laws of reflections are satisfied. So as I said, there are 2 very common existing heliostat. One is called this azimuth elevation, which is this one. And you can also have something called as a target aligned or spinning elevation heliostat. So in the target aligned, so the one of the axis is always pointing to the target. Okay. So both of these are basically rotations about 2 perpendicular axes. Okay, so it is similar to the Euler angles which we have looked at in much earlier in this course. So by doing these 2 rotations, or by doing a sequence of 2 rotations, I can track the sun. That is the basic idea. So the limitations of existing heliostat is that I cannot have very big heliostats. Okay, so it is supported at one point. Okay, the azimuth and elevation axis, there is one motor which is vertical axis and one which is perpendicular to that. So effectively, the whole mirror is supported at one point. Okay, and the deflection due to wind loading or self weight can be larger. So there are limits on the deflection. We cannot have more than 2 to 3 milliradian due to wind loading or self weight. So out of the 5 milliradian error budget, 2 to 3 is due to the wind loading and the self weight, deflection due to that. And we need to operate this heliostat up to a wind speed of 10 meters per second. Okay, it should operate as if nothing is there, and it should be surviving up to wind speed of 22 meters per second. Okay, So we need to design these heliostats such that these loading conditions can be satisfied. Okay, so if you have a single point contact, we need a large amount of backing or supporting material to avoid this deflection. So as you can see in this sketch, if it is flat, it will go to the receiver. If the tip is bent due to this deflection, the deflected beam will go somewhere else. Okay. The other important challenge or existing heliostats is that we need very accurate and expensive speed reducers. Okay, typically DC servo motors, as we have seen, rotate best at something like 2000 RPM. Okay, but however, we need the mirror to track 180 degrees in 12 hours. So we need about 15 degrees per hour. Okay, remember, per hour. Okay, so hence we need a very, very large speed reduction. So simple calculation can show that the speed reduction should be of the order of 1:to about 15,000. Okay, if you make a gearbox with this kind of speed reducer, and also maintain very good accuracy. We don't want too much backlash and friction and all those things, which reduces the performance. Then it will become very expensive, and then we will not be able to compete with other sources of energy, which is also one of the reasons, because of these gear reducers and motors and various other things, the heliostat is one of the most expensive thing. All the heliostats together make up a large percentage of a solar field, cost of a solar field. So what we had proposed, and one of the PhD students had proposed, was to use a parallel mechanism for sun tracking. Okay, so there are many advantages as a parallel robot. So one of the main advantage of a parallel robot is it is supported at several places. So hence it can carry more load. Okay, hence it can carry larger mirrors. And since it is supported at more than one point, it can deflect less. And hence it can use less supporting material, structural supporting material. So what we proposed was a 3 degree of freedom 3 RPS manipulator. So basically this is the top moving platform, as we have seen about the 3 RPS manipulator. This is the top moving platform. The bottom platform is fixed. There are rotary joints at the base, and then there are the sliding joints at each leg. And this S1, S2, S3 are spherical joints. Okay, so we can use linear actuators, okay, and we do not need expensive speed reducers. So this P1, P2, P3 prismatic joints are linear actuators, which can give you this translation in this linear actuators. Okay, so a little bit more of geometry. So typically in this field, the z-axis is along the zenith. So this is a fixed reference coordinate system, which is x, y, and z-axis. The origin is at some place in the field. So x-axis is typically always along the east, y-axis is along the north, and the location of the 3 RPS robot fixed reference coordinate system, which is O1 at O1, and x1, y1, z1 is at a distance d and some angle psi. Okay, so these are the parameters that we require to model this 3 RPS robot for sun tracking. Another important fact is there is one extra actuator. Okay, so we have P1, P2, P3, which gives you 3 different translations. However, we know that the sun tracking requires only 2 degrees of freedom. Okay, east-west motion and a little bit north-south. So there are 3 principal rotations: rotation X, rotation Y, and translation along Z. The 3 RPS robot can be shown to the top plate can rotate about X and Y and can go up and down. It can go up and down is very easily seen. So if I can move all these 3 actuators equally, it can go up and down. So if I move 2 of them and don't move this, then it will rotate about some axis. And similarly, if I move the other 2, it will rotate about some other axis. So this is a redundant system as far as sun tracking is concerned. So hence we need to make use of this redundancy. So what we do is we keep ZC constant. So ZC is the location of the center of the top platform constant. Okay, there can be other ways of making use of this extra degree of freedom, but in this case we had used ZC as constant. So the kinematics of this 3RPS robot was discussed a little bit earlier briefly, but let's go over it once more. So basically what we have is we are given the location of the sun in the sky, and what we want to do is we want to obtain the orientation of the plane of the top platform or the mirror, and then we want to translate the joints to achieve the desired orientation. Okay, so what is the desired orientation of the top platform? Such that the incidence angle should be equal to the reflected angles. The normal should bisect these two rays. Okay, and hence we have to move the normal. Okay, so the normal determines the orientation of this mirror. So if I want to orient the mirror such that it obeys these laws of reflection, we need to move the normal. So the algorithm is quite straightforward. Okay, so we choose ZC arbitrarily because it's a redundant degree of freedom. So we choose some value. From the laws of reflection, Gn is equal to Gs plus Gr divided by this. So Gn is this vector Gn. Okay, so this is the center of the top platform mirror. Gn is the normal, Gs is the vector towards the sun, and Gr is the vector towards the receiver. Okay, so the laws of reflection says that Gn will be Gs plus Gr divided by this magnitude. So again, equal angles. Okay, the reflected beam and the incidence beam should make equal angle, and all three vectors should lie in a plane. The orientation of the top platform can be given in terms of X, Y, and Z axis in the rotation matrix. We are going to denote them by N, O, and A. Okay, so N is one vector, X axis, O is the Y axis, and A is the normal to the plane. So we know that N1 square plus N2 square plus N3 square is 1. So basically this is a unit vector. This is also a unit vector. We also know that these three vectors form a orthonormal matrix. Okay, so they are perpendicular. N dot O will be 0, O dot A will be 0, okay, and N dot A will also be 0. And A is the normal to the plane. Okay. So in this 3RPS configuration, we also introduce three additional constraints. So if you think about it, we can show that the Y of C, which is XC, YC, ZC at the center of the top platform, YC plus N2 into RP should be equal to 0. Okay, so what is RP? Okay, so RP is some distance from the center of the top platform to, let's say, the 3S joints. So here we are assuming that this forms an equilateral triangle. So RP is this distance. Then N2 should be equal to O1 and XC should be equal to RP by 2 N1 minus O2. Okay, so you can think about it and we can see that it introduces these three constraints. Okay, so basically what we have is 5 constraint equations from the axis of this rotation matrix, X, Y, and Z axis in terms of N, O, and A with elements N1, N2, N3, and O1, O2, A3, and A1, A2, A3, and so on. Okay, and 3 others. So basically we have 8 equations in 8 unknowns. Okay, where are these 8 unknowns from? What are the 8 unknowns? So basically we have 3 here, N1, N2, N3, O1, O2, O3, and A1, A2, A3. But A1, A2, A3 is the normal, which we know or which we want. And then XC, YC, ZC. Okay, so we solve because ZC is chosen constant. Okay, so it is 6 of those from rotation matrix and 2 XC and YC. Those are the 8 unknowns. We use elimination theory to obtain 2 equations in 2 unknowns. xc and yc, and we solve numerically for xc and yc. Okay, so once xc and yc is known and the elimination procedure is followed, we can back substitute and find out all the elements of the rotation matrix and the xc and yc. Okay, so once we know the elements of the rotation matrix and xc and yc and zc is chosen, so then we can find the location of the three spherical joints S1, S2, S3. Okay, and then we can find the leg length because we know how much to move the leg length to achieve the location of the spherical joint. So what is the leg length? It is O1 Ri minus O1 S1 Si. Okay, so let's go back and see once. So this leg length will be O1 into Ri. So let's say O1 R1. Okay, minus O1 Si. So a vector from O1 to S1 minus O1 to R1 will give me this vector along the leg length. So similar geometry and similar equations we have derived in the past for many parallel robots. Okay, this is the way to locate the spherical joint and find the leg lengths. Okay, so once we know xc, yc, zc and the rotation matrix, then we can find the spherical joints S1, S2, S3, and then we can find the leg lengths, which is this magnitude of the difference between these two vectors. Okay, so once we have this algorithm ready, we can do some simulation. Okay, so these are some simulation results for the motion of the sun and the values of the leg length for a particular day, which is May 6, 2013. Many others were done, but this is a nice picture. So this is why I have chosen this. And then we can compute L1, L2, L3 for this as the sun is moving. So here are 4 snapshots. One is the sun has moved from here to here. The red is the normal, the reflected beam, which is fixed because the receiver is located fixed. As the sun is moving, you can see that the red, the normal is changing, okay, and hence the mirror orientation is changing. And for each of those instances, we can discretize this motion of the sun, and then we can find out L1, L2, L3 by that algorithm which I discussed just a few slides back, last slide. Okay, so let's look at some simulation. So these simulations were done in MATLAB. So we compute all these quantities, we compute the normal, we compute the motion of this sun, which is known, which is given, and then we show how the normal is moving. Okay, so you can see that the blue is the reflected beam, which is always constant, red is the normal, and the black is the direction of the sun. This is a more detailed picture, zoom picture, which says how the legs are changing, okay, as the sun is moving. Another view of the whole of the thing, that you can see that this is the mirror, this is the 3RPS robot, how it is orienting when the sun is moving, such that the reflected beam is at the same place. One of the things which I said was this parallel robot can take more weight, okay, because it is supported at 3 points. So this analysis was also carried out. For this, we need to do a finite element analysis. So we have a CAD model of this mirror and the 3 support points and the backing structure in SolidWorks. Then we do this FEA. So we need to assume some weight of this mirror. It turns out this is of the order of 10 kg per meter square. The wind load is for the maximum load. We want to make sure that this mirror will survive, which is 22 meters per second. Okay, so this is the CAD model. So we have these 3 legs. This is the mirror and this is the support structure at the back. And the worst case is when the wind is coming directly normal to this mirror. Okay, so for a uniform wind load, the pressure is half CD rho V square, and we also do a factor of safety, in this case 2. So we solved this problem for different wind speeds, for different dimensions of this mirror. We took 2 by 2, 3 by 3, 5 by 5, and then we found what is the maximum deformation due to the wind and the self weight. And we also tried the existing azimuth elevation configuration, which means basically it is supported at 1 point, and this 3 RPS configuration, which means it is supported at 3 points. So what you can see is there are some deformations for 2 by 2, which is 1.8862 millimeters, whereas at 22 meters per second, it is 4.7281 millimeters. This is the maximum deformation. In the azimuth elevation, in order to meet that pointing accuracy requirement, okay, we need to put a frame in the azimuth elevation which weighs about 21 kgs approximately for 2 by 2, whereas as the area becomes bigger and bigger, okay, you can see that the supporting weight will become very large. So this is like 1300 kg. The maximum deformation is such that it will still point to the mirror. The mirror will still reflect the beam to the receiver. In the case of a 3 RPS robot, the weight does not increase so much. Okay, it is because it is supported basically at 3 points. So to achieve the pointing accuracy with a 3 RPS robot with wind at 22 meters per second, we need only 535 kgs of structural material. Okay, so if it is a small mirror, it is 21 in azimuth elevation and 15. But if it is a large mirror, 5 by 5 meters, okay, then we can see it's a significant reduction. So the supporting frame weight reduction lies between 15 and 60%, okay, in the case of a 3 RPS heliostat. So this mirror was designed, analyzed, and then we built one such hardware, one sun tracking hardware. So how do we test it in the lab? So for the azimuth elevation and also for the 3 RPS, basically what we did was we don't have the sun in the lab. So what we do is we invert the problem. So instead of the sun moving and the reflected beam at the same place, pointing at the same place or reflected to the same place, the sun here is stationary. Okay, so we have a laser which is pointing to the mirror, which is this red spot, and then we move the mirror such that this beam follows some path on the roof. So this path on the roof is basically the path of the sun, okay, on a particular day and time and so on. So you can see these dots. So these are the simulated or equivalent locations of the sun. So hence, if I can move the mirror properly, it will get reflected onto this laser, okay, the stationary receiver. So let's show 2 videos. So as you can see in this case, this reflected beam is moving along the roof of the lab, and it should be approximately the place where the red spot is the location of the sun. Okay. So we also manufactured the 3 RPS configuration. So for the 3 RPS configuration, the spherical joints were basically spherical joints from some scrap or automobile shops. So you can see they're not very sophisticated and fancy. The prismatic joints, these actuators were bought, and then we have some encoders terminals at the base. So we can measure the rotations of the motors which are implementing prismatic joint. So basically the prismatic joint has ball screws. So we rotate the one of the items and the nut will go up and down. Okay, so we can measure the rotation of the ball screw by means of these encoder terminals. So this is an experimental result, actual experimental result of the 3 RPS robot which was built, and the azimuth elevation drive or heliostat which was built, and we can see how they perform. So this is on some day at some time in top of the roof of one of the buildings in ISC. So as you can see, it is both of them are reflecting at some place. Okay, ideally they should be reflecting at the same place, but just to show that both are working, we have just purposely made sure that it is focused on two slight close by spots. Okay, so as you can see that the images are not exactly at the same place all the time. It should be in an actual field, and the problem is because of all the inaccuracies in manufacturing and control. So now you can see more or less at the same place. If it is cloudy, you don't see any image. So at this place, at this point, you can see the two images are very close to each other. So at 3:30 p.m., you can see both of them are at the same place. Okay. So we tried this from morning till about 3:30, 4 o'clock. Because after that the sun goes down too much and you cannot focus the beam onto the receiver. So we built the sun tracking devices using a 3 RPS heliostat and an azimuth elevation heliostat. The pointing errors, as you can see in the video, are much larger than 5 milliradians. Okay, so they are of the order of 20 to 30 milliradians. Okay, you should keep in mind that these are not professionally made heliostats. They were made by students. So the main cause of this error are manufacturing and initial settings, okay, which can be improved. We can also build another parallel robot for sun tracking, and I will show you why we thought of building this parallel robot. This is this 3 UPU manipulator. Okay, so previously it was 3 RPS, so there's a rotary joint, prismatic joint, and a spherical joint. In this case, each leg is a hook joint or a universal joint, a P joint, and another U joint. Okay, so there are 3 actuators, 3 P joints, and there are 2 passive U joints in each leg. It's a 3 degree of freedom robot. You can verify using the Grobler-Kutzbach criteria. This 3 UPU manipulator has very special axis geometry. Okay, the 2 intermediate R axis. What do you mean by 2 intermediate R axis? The U axis, U is a 2 degree of freedom joint. So basically it has 2 rotary joints perpendicular to each other. So I have one rotary joint, a second rotary joint which is perpendicular to the first one. Then I have a prismatic joint. Then I have another rotary joint and the fourth rotary joint which is perpendicular to that also. So the 2 intermediate joint axes are set parallel, are designed to be parallel. And the first and the last rotary joint axis intersect at a point. So this is called as the stationary center of rotation. So this is the way it has been designed. Okay, so this is the picture. So the first and the last are intersecting at a point. For each of these 3 legs, that is what is happening. And the second and the fourth R, this is the second and this is the fourth R, they are parallel to each other for each of the legs. Okay, so in this special configuration, okay, you can show that this top platform has only 3 rotational degrees of freedom. Okay, so this is a spherical wrist. So this is again in a little bit more detail. The first joint and the last rotary joint are meeting at some center point, which is the center of rotation. Okay, and it is stationary. The second rotary joint and the third rotary joint are parallel to each other and perpendicular to these rotary joints. Okay, so this was developed by several researchers because it is a spherical rest. So this top mirror can now rotate about this stationary center of rotation. Okay, so hence what you can derive the kinematics of this 3UPU sun tracker. Again, the basic idea is this Gn, okay, which is G normal, is given by G to the sun and G to the receiver, this sum of two vectors divided by the magnitude. The orientation of the mirror with respect to the base is given by this N, O and A is the mirror normal Gn. Okay, so we can obtain the other two columns of R for azimuth elevation and TA modes. So what should be the N or x-axis and the y-axis? That depends on the azimuth elevation or the TA or the target aligned mode, the two standard configurations which I had discussed right in the beginning. Okay, so in the azimuth elevation configuration, we have two consecutive Euler angles. The first one is rotation about z by this azimuth angle, and then rotation about y by pi by 2 minus the elevation angle. Okay, and the rotation matrix resulting from these two is given by this R Az El. So you have cos theta Az, sin theta El, 0, and some sin theta El, and so on. The last column is the mirror normal, which we know. Okay, we know where the receiver is, we know where the sun is, and hence we know what should be the mirror normal. So hence, comparing the mirror normal with this last column, we can find the elevation angle and we can find the azimuth angle. Okay. In the target aligned case, we have two rotations again. So one rotation is spin about G to R, center of to the receiver. As I said, it is always pointed towards the receiver. And the rotation about Ym by an angle, elevation angle. So the rotation matrix obtained by these two consecutive Euler angles is this horribly complicated rotation matrix. Nevertheless, basically what you can see is there is some C psi, C lambda, theta special, and all spherical, various things are there. The last column is the mirror normal. Okay, so comparing the last column with these expressions, again we can find this theta sp, okay, which is the spinning angle and the elevation angle. Okay, if you can go and see the actual paper if you want the real detailed steps. Nevertheless, we can find basically the rotation matrix either in the target aligned mode or in the spinning azimuth elevation mode. So once you know the orientation of the top platform, we can find the location of the U joint in the top platform, and the location of the U joint in the bottom platform is obviously known in terms of the radius vector. So we assume that these 3 points at the bottom platform, 3 U joints, lie on a equilateral triangle, okay, with a radius of RB from the center to one of the corners of the equilateral triangle. So hence B1 is RB00, B2 is minus 1 by 2 RB, root 3 by 2 RB, and so on. Likewise, the top hook joint or universal joint is located at RP. We assume that the top triangle is inscribed in a radius of circle RP, equilateral triangle, and again we can find this UT1, UT2, UT3 from the center of the top platform. The position vector of the top platform, the center of each of these hook joint, can be obtained by a transformation matrix. Okay, so transformation matrix into GUTI with some 1 added, because it's a 4 by 4 homogeneous transformation matrix. We can find this out. And what does this T contain? This T contains basically the orientation of the top platform and the location of the center of the top platform, which we know. Okay, the center of the top platform about which it is rotating is fixed, and orientation can be obtained from finding the theta sp and the theta elevation. Once we know the location of the hook joints in the top platform, we can find the leg lengths. Okay, Li is nothing but the vector to the top platform, vector to the base, and the magnitude of the difference of those two vectors. Okay, so we can compute this leg lengths, and then we can find what is the actuation required to achieve orientation of a mirror at the March equinox at Bangalore. Okay, so at 9 a.m. it looks like this, 12 noon it looks like this, 2 p.m. it looks like this, 5 p.m. it looks like this. At any other time we can find what the 3UPU robot looks like. Okay, and we can compute the leg lengths. So L1 is this red, blue is leg 3, and green is leg 3. So what this plot is telling you is that if I change the leg lengths from, let's say, 8 a.m. to 6 p.m. in the evening in this manner, the mirrors will orient in a way such that the reflected beam is always at the receiver. Okay. So this was the configuration of 3UPU in the target aligned mode. Okay, when we operate this 3UPU device in the target aligned mode. We can also compute the leg lengths in the azimuth elevation mode on the same day. Okay, again on the March equinox. So what you can see is this leg lengths change differently. Okay, so again remember we have 3 degrees of freedom, L1, L2, L3. However, we need only 2 of them. So this is a redundant device and we can use it in whatever way we want. So we can use this redundancy in a suitable way. So first we configured it to be in the target aligned mode, and then we configured it in the azimuth elevation mode. Okay, so 2 different ways of successive Euler angles. Okay, so why do we do all this? So one of the main important reason is that the sun tracking using azimuth elevation and target align is different. Okay, and what way is it different? If you see the image which is on the receiver using target align and using sun tracking, so this is red is target align, AZ is the other one, and this blue cyan line is the receiver. So what you can see is the image looking differently if you track it using the target align mode or if you track it using the azimuth elevation mode. So sometimes the image is going out of the receiver, okay, and for example you can see a small quantity here and a very small quantity here, but the small quantities are different for the 2 different configurations. Okay, so this is the plot of this spillage, which is how much area is outside the receiver for target align, which is this blue, and azimuth elevation, which is this cyan. Okay, so as you can see, the cyan one is smaller for March equinox. Okay, so likewise at December solstice you will get a different amount of spillage. Okay, so how much is this spillage? This is very small. Okay, so the difference in both of them would be like maybe 3 to 5%. But even that is very important when you are doing sun tracking and when you want to concentrate the energy onto the receiver. So what the idea is that since we can run this 3UPU manipulator in either in the azimuth elevation or target align mode, we can switch electronically depending on the time of the day and the date of the year where the spillage losses is less. Okay. So this is a CAD model of the 3UPU sun tracker which was built. So basically this is the bottom platform. This is the way we can implement this 2 rotary joints to be parallel and 2 other rotary joints to meet at a point. So it turns out that these rotary joints meet at this fixed point, which is a little bit above the plane of the mirror. Okay, this is due to manufacturing and design and so on. We cannot have the fixed point on the mirror itself so easily. So the center of rotation is a little bit above the plane of the mirror by about 144 mm. And these distances are chosen, and this angle is 150 and so on, and this is 500 mm. So this was built, okay, and the plan is that we are going to switch between azimuth elevation and target aligned configuration depending on when the spillage losses is less. And this is done using computer. There is no change in the hardware. Okay. So this device was built, as you can see that this is the leg. This is one U joint. There's another U joint at the top. And since the point of rotation is above a little bit, so we have placed the mirror a little bit above the place where the hook joints are. Okay, so center of this mirror is actually the center of the rotation. So we carried out some experiments, and this is the result of one experiment, which shows that at 3:18 p.m. on May 24, 2017, okay, when the 3 UPU was operating in the azimuth elevation mode, the image was here. Okay, it took about 1 or 2 minutes for the students to run the other program, which is the target aligned mode. So at 3:20 p.m., the image is here. So as you can see, it is more or less at the same place. Little bit of difference is there. Okay, so that is also due to the error. So these are some of the geometry. So this is about 6.7 meters away from the center of the mirror. Okay, and so on. So what this experiment is telling you is that we have a 3 UPU sun tracker which can be switched between TA and azimuth elevation mode electronically. Okay, and why do we want to do that? We want to reduce spillage losses. So in conclusion, we have a novel use of a parallel manipulator for sun tracking. Okay, there are several kinematics and design challenges. The motors have to rotate very, very slowly and also very accurately. There are also lots of advantages using a parallel robot. We can carry more load. Basically, we can carry bigger mirrors. We can use low-cost linear actuators. It is also potentially more accurate because the deflections are less. And it is reconfigurable because we can use the redundant degree of freedom in this 3 UPU to switch between target aligned and the other one is azimuth elevation. Okay, so both these sun trackers were built at ISC by students, so there is a significant need of improving these. So we need to basically remove the play at the joints, and we need to do better manufacturing.